Welcome to the class. We were discussing about the blade design and cascade theory. In the last class, we had seen that how a blade of cascade can be mounted in a tunnel, which is a blower type tunnel. What are the different parts of a blower type tunnel, or rather cascade tunnel, where it is mounted, and then what are the different properties we measure, how do we measure direction of velocity. These are the things which we had seen. Now these are the parts and this is the process in which blades are designed. We are going to see the further things which are involved in the cascade theory and blade design process. So, what are the parameters or cascade variables? Means in the cascade tunnel, once we mount a cascade or row of blades, what are the variables which can be used to change the effect, used to see the effect. One is obviously Reynolds number. We know Reynolds number by definition is Re is equal to rho Cl by mu, where rho is density of the flow, C is velocity, L is chord length, and mu is viscosity of the flow. Here we have to do experiment while designing a cascade or blade with different Reynolds number, different Re, and these experiments with different Re can be done by varying C, which is velocity, or we can vary L, or we can vary the density if we are working with compressible flow. But if we are working with incompressible flow, we cannot vary the rho which is required, or we need to go with high pressure gases for the expansion, not just the atmospheric gas. So, second variable which is there, which is Mach number. Mach number by definition M is equal to C by A, where we know A is speed of sound and it is equal to square root of gamma RT. Gamma is specific heat ratio, R is particular gas constant, T is the temperature at which we are finding out the A. Now, as we see, Mach number involves C, Reynolds number also involves C. So, prominently Mach number variation can be obtained by varying Reynolds number, but to vary Mach number independently of Re, we need to change density, and this is a tough task. Third variable which is there for in the cascade variables is pitch to chord ratio. We know chord is the distance between leading and trailing edge of the aerofoil. We are going to see these terminologies. Further, pitch is the spacing between two blades in the rectilinear cascade. So, this pitch to chord ratio is one more parameter in the cascade variables, and this is S by L, where S is equal to pitch and L is equal to chord, and then this to vary we need to vary basically the spacing for given geometry that is L, we can vary S by L by varying S. Here we can dismantle the cascade where we would have put multiple number of blades, and now after dismantling we will reassemble the cascade by altering the spacing between the two blades. So, this is how we can vary the pitch to chord ratio. Fourth is aspect ratio. Aspect ratio is for a particular blade which is defined as H by L, where H is height of a blade and L is chord. So, H by L is the aspect ratio. We can vary aspect ratio by varying H or by varying L. For a given geometry, again we cannot vary L, so we have to vary H. H is the height of the blade which we can vary, but we know that this cascade would be mounted at the end of the tunnel, and then we have to vary the test section and the contraction. For that all sake, where we are interested to vary the aspect ratio through variation of the blade height. This is a tough task. Then fifth variable is blade geometry or profile. In the process of blade design, we should test different blades for their performance for a given turbomachinery application. So, the profiles or geometries of the blades which we would have decided, which we would have defined, and those geometries or those blades should be tested in case of their testing in the cascade tunnel. So, we should vary the geometry or what we say it as the profile of the blade to assess its performance. So, next variable is boundary layer. And turbulence. We have seen here that the cascade receives the boundary layer from the contraction and the test section. It is invariant how would be the perfect contraction we implement, we still would have certain thickness of the boundary layer which is received by the cascade. We have also seen that we put porous walls so as to remove the decelerated flow. So, to see the effect of boundary layer which is received by the cascade, we can change the porosity of the material which would be actually absorbing the decelerated flow. By that we can vary the thickness of the boundary layer received by the cascade. Further, we can vary turbulence or intensity of turbulence which is present at the entry to the cascade. For that variation of turbulence, we can do few things where we can put different kind of turbulent generators, and those turbulence generators can be for variation of turbulence. We can put different turbulent generators such as the turbulent grids upstream of the cascade, and those turbulent grids can generate different amount of turbulence received by the cascade. Further, the type of the boundary layer is also governing parameter which can again be laminar or turbulent, and that depends upon the Reynolds number. So, Reynolds number is the first parameter as the cascade variable. Here, if we vary the Reynolds number, that itself would vary the amount of turbulence or maybe the nature of the flow which is received by the cascade. Then seventh variable is incidence or incidence angle. incidence angle is the angle which the blade makes with the velocity vector. So, this angle can be varied by multiple ways, and here one of the simplest ways is to the giving angle to individual blades, where individual blade will be clamped or pinned in the test section, and once we are interested to change the incidence of the blade, we will change its mounting in the test section, set it to the desired angle, and then this would be continued for all the blades, and then all the blades would be set for the desired incidence angle, and then we can test it for the different incidences. So, first A is by changing angle of a blade. Then second option over here is having sliding walls. So, second option is sliding walls. In case of sliding walls, we can do different arrangement, that we know that this is the test section of the cascade tunnel, and then in this test section we can keep the sliding walls, and then this cascade will be mounted at the end of the sliding walls. So, this is the conventional way by which we would be mounting the cascade. So, this is velocity vector, and then this is the direction in which cascade is at this moment mounted. But this wall and this wall, if we can keep adjustable, then we can change the orientation of the cascade and hence the inclination. Then there is one more option, which is for continuous change in inclination or incidence, continuous change in incidence. Here cascade is mounted on a pivot and which is operated continuously, such that the orientation of the cascade would change with respect to the flow. So, this is cascade now. This cascade would be put on a pivot, and this pivot is rotating the cascade So, this is adjustable wall, and this is also adjustable wall. So, these two are adjustable walls, and then this is a movable box, and then this is pivot on which the cascade is connected with. So, this pivot would rotate the cascade in different angles, and then it will change the orientation of the cascade with respect to the velocity vector, and hence it can alter the incidence angle of the flow. Now this all was related to the testing of a cascade in a tunnel, and then that tunnel we have talked with about is the cascade tunnel. So now we have understood what is a cascade tunnel, what are the different ways by which we can measure different things in a cascade tunnel, and also how to alter different variables or performance parameters for a cascade in a cascade tunnel. Now we will see few things related to blade, and then we will see how the turbine cascade will be there and how the compressor cascade will be there and what are their basic parameters for the derivation. So let us see for the blade, we will see, and we will see first aerofoil nomenclature. In case of it, we first draw a symmetric aerofoil, and this symmetric aerofoil has this as the axis, which is also called as the chord. If we measure the distance between the leading edge and trailing edge. So this, if we take it as y axis, and this if we say it as x axis, then this is the location of maximum thickness, and then this maximum thickness is going to appear at a particular distance, say a dash, and then this is chord. So this x axis is basically defined as the x location divided by maximum x location, which is chord. So this axis is x by L. So parallelly y axis would also be normalized with L as y by L. Having said this, there is no curvature in the aerofoil. So if we have curvature in the aerofoil, then same y by L and x by L axis. So this aerofoil with curvature is this. So this time this is curved central line is called as camber line, and then this is leading edge, this is trailing edge. So we will say it as LE and TE, and this is the maximum curvature. So this is called as maximum camber location of the aerofoil. So these are the nomenclatures of aerofoil cross section. Basically the turbine blades or the compressor blades will have a particular specific cross section, and those cross sections are generally aerofoil kind of cross sections, since aerofoil is a shape which is preferred since it gives least drag and it gives us desirable lift. It can give for a particular shape, it can give good lift and with lesser drag. It is a streamlined object. And then different labs all over the globes have defined different aerofoils, such as there are European aerofoils, NACA aerofoils, and then those aerofoils would have different shapes, and those shapes would have different performances since they are defined for their own applications. So we can use either such aerofoils or design new aerofoils for the applications of ours for the turbo machine. Now we will see turbine cascade. By saying turbine cascade, we are saying that the turbine blades are put in the tunnel in a specific order, which is called as in the rectilinear tunnel, a rectilinear cascade, in a specific order of spacing, which we have specific geometry, chord length, and then specific camber. So that blade is kept in a tunnel, and then how that cascade would look like, that is what we are seeing over here. So this is having certain nomenclature again. So let us first plot the cascade. So we know we have to put multiple number of blades while thinking of a cascade in the tunnel. So here first let us say that this is the chord line, and so that this is leading edge and this is trailing edge of the aerofoil, and then this is the camber line of the aerofoil. And since this is camber line of the aerofoil, we should know what are the different angles. So this camber line we can draw a tangent at the leading edge. So this is tangent at the leading edge, then we can draw a tangent at the trailing edge. So if we draw a tangent at the trailing edge, both the tangents would meet at a point and then they make an angle theta, which is called as a camber angle. But this tangent at leading edge, so this is the direction of flow for us. So flow is coming from this. So this is, that is why this is the leading edge and this is the trailing edge. So at the leading edge the tangent makes an angle. So this is chi 1, and then at the outlet it is making an angle, this is chi 2. So this diagram is called as the diagram for camber angles. Now we will draw a diagram for blade angles. We have seen in case of cascade or in case of turbines or in case of compressors, while drawing the velocity triangle, there are certain blade angles, there are certain nozzle angles. So in those terminologies equally we are making the blade angles and camber angles. So blade angles over there was the angle for the relative velocity. In the cascade tunnel the blades are stationary, so the velocity, absolute velocity, is going to make certain angle, but these blade angles over here are defined in a different way. We are just going to draw that. So this is, suppose, again the axis. So this is our aerofoil. Now this is the camber line. So for the camber line, again we can make one tangent at the inlet and we can make one tangent at the outlet. So having said this, so this is the line which is joining the leading edge and the trailing edge. This is the chord line. So this line joining leading edge and trailing edge will be making certain angle with the vertical axis, and then that angle is called as stagger angle gamma. And we have seen that the tangent making an angle with the chord line, we are already calling it as chi 1. So this angle, which is now chi 1 minus gamma, is called as alpha 1 dash, which is a blade angle at the inlet. So similarly we can make this tangent with vertical axis as this tangent with the chord line as chi 2, then this vertical line with the tangent as what we made over here as alpha 2 dash, and then we have this small angle as the stagger angle. So, these are the blade angles alpha 1 and alpha 2. Now, we will show the same blade where we will add the velocity vector. So, this is our aerofoil and this is the camber line of the aerofoil. So, this is the vertical line here, this is the vertical line here. Now, this is the direction of tangent, and then let us feel that this is the way by which flow is approaching, and this is the C1 absolute velocity vector. So, and then we have the chord line as this. So, velocity vector making an angle with chord line is alpha 1, which is called as air angle. Similarly, let us feel that the velocity vector is going here as C2. So, this is making an angle with the vertical line is alpha 2. We know what is alpha 1. Alpha 1 is the angle made by the tangent with the vertical line. So, this is alpha 1, rather alpha 1 dash. Similarly, we can show here and that this is the tangent which is making an angle which is alpha 2 dash. So, in this fashion we would have different angles defined. We will revisit these angles again. So, we will say here that alpha 1 dash here is the blade angle, alpha 2 dash is the blade angle at inlet, it is also blade angle at outlet. Then we have theta, which is blade camber angle. This angle is made between two lines which are tangent at inlet and outlet. So, this is camber angle at inlet, then chi 2 camber angle at outlet. Then we have alpha 1 and alpha 2 which are air angles. So, alpha 1 is air angle at inlet, alpha 2 is air angle at outlet. Then we have gamma, which is stagger angle. Then we have new angles which are defined. One is I is called as incidence angle. We will define it. Then we have delta, it's called as deviation angle. And then we have epsilon, which is deflection angle. We will see these three angles. Before that, we will revisit how we have got these angles. We got alpha 1 dash and alpha 2 dash as two angles which are between the axial direction and tangent to camber line. So, if we go back, we see that alpha 1 dash and alpha 2 dash, these two are the angles between the axial direction. So, this is the velocity vector. This velocity vector has two components, one is cx1 and other is cy1. So, this is the direction which is of cx1, so axial velocity, or in our language this is ca1, which is the axial direction of velocity. So, the angle made by the tangents with the axial direction is what? Alpha 1 dash and alpha 2 dash at the inlet. Theta is the angle between two tangents to camber line. Then chi 1 and chi 2 are the angles between the chord line and line tangent to camber line. We can see this. So, this is the tangent at the leading edge, this is the tangent at the trailing edge. Both the tangents meet at theta, which is tangent angle. So, chi 1 is the angle between chord line is a straight line which is joining leading edge and trailing edge. So, this straight line makes an angle chi 1 with the tangent to the camber line at the inlet and chi 2 to the tangent at the outlet. Same way here the chord line is inclined. So, this chord line over here is perfectly aligned with axial direction. Here chord line is not perfectly aligned with the axial direction. So, we have chi 1 made with the straight line joining leading edge and trailing edge and the tangent. So, this alpha 1 and alpha 2 are the angles between velocity vector, absolute velocity and axial direction. We have seen this. Absolute velocity c1 makes an angle this with the absolute velocity with the chord line. So, we have seen this, that the absolute velocity c1 is making an angle alpha 1 with the chord line, which is called as air angle. Similarly, this is with the same at the outlet. Alpha 1 is the angle made by the velocity vector with the vertical line or the axial direction. So, this is alpha 1. So, similarly, alpha 2 was the angle made by the velocity vector with the vertical line. So, these are the angles. Having said this, so it is with the axial direction. Now, gamma is the stagger angle. Now, this stagger angle is between the chord line and axial direction. If we see, it is the chord line, straight line joining leading edge and trailing edge and the axial direction. So, this is the gamma, which is stagger angle, and this stagger angle is used for the setting of the cascade into the tunnel. So, it is mostly a experimental number which is used for the convey. So, then we have new angles which are defined, and then incidence angle I is basically defined as air angle at inlet minus blade angle at inlet. So, it is alpha 1 minus alpha 1 dash. So, alpha 1, if we see, then it is the angle between the axial direction and absolute velocity, and then alpha 1 dash, which is the alpha 1 is the air angle, alpha 1 dash is the blade angle between the tangent at the inlet to the camber line and the axial direction. So, this alpha 1 minus alpha 1 dash is this small angle, and this small angle is incidence angle. Then we have delta, and this delta is called as deviation angle, and then this is delta is equal to blade angle at outlet minus air angle at outlet. Hence, it is alpha 2 dash minus alpha 2. Same way over here we can see alpha 2 dash minus alpha 2. So, this is alpha 2 dash, which is the angle between the tangent to the camber line and the axial direction, and then C2 is the velocity vector. So, velocity vector and the axial direction, this is alpha 2. So, having these two difference here as delta, which is the deviation angle, and deflection angle, which is epsilon, is equal to air angle at inlet plus air angle at outlet. So, this is alpha 1 plus alpha 2. So, if we see that air is coming in this direction at the inlet, and going in this direction at the outlet. So, air is getting deviated or rather deflected by a complete angle, which is alpha 1 plus alpha 2 between the inlet and the outlet. So, this is deflection angle. Now, we have one more thing to remember over here, that we define theta, which is camber angle, and it is chi 1 plus chi 2. Similarly, alpha 1 dash is chi 1 minus gamma. We can see, so chi 1 is the angle which is here, and then this is gamma. So, chi 1 minus gamma is alpha 1 dash. So, we are writing alpha 1 dash is equal to chi 1 minus gamma. Similarly, alpha 2 dash is equal to chi 2 plus gamma. We can go at the outlet and see. So, this is chi 2, this small angle, this is gamma, and this is alpha 2 dash. So, alpha 2 dash is summation of two angles. So, now if we make alpha 1 dash plus alpha 2 dash, then we get chi 1 plus chi 2. So, camber angle is alpha 1 dash plus alpha 2 dash, which are blade angles, and then which are equal to chi 1 plus chi 2, which are camber angles. Now, we can write one more thing for deflection angle, which is alpha 1 plus alpha 2. So, alpha 1 is alpha 1 dash plus I, and alpha 2 is alpha 2 dash minus delta. So, epsilon is equal to alpha 1 dash plus alpha 2 dash plus I minus delta. So, from here we can write it is equal to theta plus I minus delta. So, this is the definition of deflection angle, or rather derivation of deflection angle. Having said this, now we need to find out what is the basically way by which the direction of forces are defined which are getting applied on a cascade, and then how to find out using the derivations which involve certain mathematical relations. We will see this in the next class. Thank you.